recording is in progress. If you want to make sure you don't appear in the recording, you can let me know, and I will like put a black box over your face if it ever shows up in the video. Okay. All right, so schemes and varieties, what are those things? In algebraic geometry, schemes are sort of the basic object you want to study. And you might have heard that algebraic geometry is about studying solutions to polynomial equations. And so a scheme is really basically just a bunch of polynomial equations. But I'll say a little more precisely what that means. So I'm also going to be really vague here. I'm not going to, talk about the Zariski topology or structure sheets or anything. I'm just going to make up some words and say some things that aren't exactly true, but capture the heart of what's going on. So a scheme is like where you have scheme is like where you have a bunch of variables and a bunch of equations. So like, for example, maybe my variables are called A and B. Or actually, let's do a fun example. Maybe my variables are called A, B, and C. And I have only one equation, which says A cubed plus B cubed equals C cubed. Okay. This pair of like variables with equations defines a scheme in some way. And that's really what the data of a scheme is. It's where you have variables and equations. And anyone who knows algebraic geometry is screaming inside right now. But this is what we're going to imagine that a scheme is. It's where you have variables and you have equations, and they have to be polynomial equations. But they could be polynomial equations with coefficients coming from really anywhere. So it would be totally fine to have some variables like x and y, and my equations are like x squared plus 3 equals 7, and xy equals I, or something like that, where I is the complex number I. The coefficients that appear in my polynomial equations can be whatever I want. And at the end of the day, all the coefficients that we use to define the equations for a particular scheme, these coefficients all have to live in some field. So these coefficients came from the complex numbers. These coefficients came from the integers. But you could start wherever you want. You have some variables that are just names for symbols. And we have some equations that are polynomial equations where I have a specific ring in mind that I'm pulling the coefficients from. I have some polynomial equations with coefficients from that ring. And when I've done that, I would say that this guy is a scheme defined over Z, and this guy is a scheme defined over C. But you could have a scheme defined over any ring. And in the chat, Jacob asks, can I have infinitely many variables for this talk? So for schemes, yes, but what I'm going to say about varieties is no. Because they have to be finite type, separable, integral, blah, blah, blah. Okay, right. So that's sort of our basic idea of what is a scheme. We're not going to make a big deal about the precise definition. A variety is going to be where I have finitely many variables and finitely many equations, and I'm over Z or a field or something like this. Okay. So the point of doing this, of setting things up in this way, is that once you have your variables and your equations, you could study the solutions in the ring you started with. I could think about solutions to this equation inside Z. And there's a famous problem about trying to figure those out. But I could also think about, solutions to this equation inside a finite field, or I could think about solutions to this equation inside the rational numbers, or solutions to this equation inside the real numbers. And there's lots of solutions to this equation in the real numbers and the complex numbers. And the reason I can think about all those things is that there's a map from Z to R, there's a map from Z to C, there's a map from Z to any finite field, and Z can map to any other ring. And so instead of thinking about these coefficients as living in Z, I could alternatively think about them as living in R, or living in C, or living in FQ. And that would be totally fine. That still makes sense as an equation with coefficients in R, or C, or FQ. And then I could think about solutions to that equation over those different rings. And Grothendieck's insight in developing schemes was that if you have this like flexible perspective, if you allow yourself to think about the solutions to a system of equations over many different rings all at the same time, it gives you a lot of power. And so the Weil conjectures are one sort of statement that's only really possible to make because of this kind of perspective, thinking about solving the same system of equations, but thinking about the set of solutions over many different rings all at the same time. On the other hand, if I had something defined over C, there's not many other ways I could think about it. There's not a map from C to R. There's not a map from C to FQ. There's not a map from C to Z. There are none of these maps. And so you can't think about solutions to this guy with living in R. It wouldn't make sense. You can't think about solutions to this guy living inside a finite field. That wouldn't make sense. So depending on where your coefficients started, you might have more or less flexibility in where you can start thinking about your solutions. And the best place to start is over Z. If I have a scheme defined over Z, every ring contains the integers inside it somehow. Every ring has integers. And so I could think about the solutions to that system of equation wherever I want. And so those are sort of the most powerful kinds of schemes, the schemes where I could think about solutions anywhere. And so when I have a scheme, let me just put some notation down. If X is a scheme and R is a commutative ring, then X of R, that should just be R, is the set of solutions in the ring R. So by the scheme, I mean sort of this pair of data, the names of variables and the syntactic equations with coefficients in whatever base ring I started with. And so if I called this guy X1, let's say, and this guy X2, then I could think about, what is X1 of Z? What are the integer solutions to the system of equations? And it turns out there's not that many. You can have like 0, X, X for any X. You can have X0X for any X, right? If A is 0 or B is 0, we get a solution that way. And it turns out that's it. That's Fermat's last theorem. Great. No, wait, maybe that's not true. Maybe they have to be positive. Okay, maybe more. I don't know enough about Fermat's last theorem. But at least there are these solutions. Okay. There are no other natural
X and negative X, 0.
Yeah. X and negative X and 0. Yeah, that's a good point. Okay, so there's more. But it has something to do with Fermat's last theorem. All right, but that's not the point of this talk. Just some basic notation for us. We're going to define some schemes, and we're going to think about these sets, the sets of solutions over different rings. And this guy is called the set of points of my scheme over the ring Z. So this is the set of points of X over R. And a nice feature is that if I have a map from a ring R to a ring S, then I could take a point of X over R, and I could get a point of X over S. If this is a ring homomorphism, and I have my solution to my system of equations, so I have like X0, X1, through Xn, the different values for my variables that solve the system of equations, I can just apply F to all those numbers. And because F is a ring homomorphism, it'll preserve all the polynomial equalities that you want it to satisfy. And I have this ring homomorphism from R to S, and so you can just check that this guy lives inside X of S. This is a really useful feature because sometimes you have a polynomial equation that's hard to solve in one place, easy to solve in another place. So let's take an example. Maybe x squared plus x equals y squared plus y plus 1. I think about this living over Z. I have two variables, x and y. I have this one equation. And just thinking about integers, good question, Roman. In this case, I actually literally mean, if you want, X is spec of base ring adjoint variables modulo equations, and X of R is the maps from spec R to X as a scheme. And those turn out to be exactly in one-to-one correspondence with actual tuples of assignments of elements of your ring to R. It's something like maps spec R to spec of my base ring adjoint X naught through Xn mod equations. That corresponds to a map the other way between the rings. And the map the other way has to send these guys somewhere. It sends them to elements of R. So the R points of this scheme, if you do the actual scheme theory, literally are these tuples. Okay, but in case you don't know what spec means, don't worry about it. It's totally useless. X of R really just means R tuples of elements of R. Those are the assignments to the variables that satisfy the equations. Okay. Okay, and so I could think about this equation, with two variables. And over Z, it's not so obvious whether or not this has a solution. You have to think about, okay, I take a square, I add the original number. Do those two kinds of things ever differ by one? Okay, the answer is no. You can check that pretty easily. But an easier way to see it is I could think about the points over Z, and I could send them down to F2, to the field with two elements. In other words, I just think about is X even or odd, is Y even or odd. And what I see is that either way, this guy is even. X squared and X have the same parity. This guy is even, and so this guy's odd, and even can't equal odd. This equation has no solutions over F2. So I have a situation where I'd have the points of my scheme over Z mapping to the points of my scheme over F2, and this is the empty set. And so this guy has to be the empty set. So that sort of reasoning can be useful. All right. Cool. So yeah, like I said, let me know if there's any questions. But let's talk about the Weil conjectures. Okay, yeah. So by variety in this sentence here, I mean a scheme that we defined by taking finitely many variables and finitely many equations and starting with an Noetherian ring. Okay. And it also should be integral and it should be separated. I guess separated is free here. It's happening. All right. So, all right, but basically, scheme with finitely many variables and finitely many equations defined over Z. All the equations have integer coefficients. So I take one of these things, and the stars, because really this should be like a smooth, proper finite type variety over Z or whatever. But more or less, we're going to take whatever this guy is, and then I can think about the number of solutions to that system of equations over a finite field. That's this guy here. X of fq to the n is the set of solutions of X over the field, over this finite field with q to the n elements. And here, q is a prime power. I'm just going to fix this number q for the rest of the talk. There's some number p, and p is prime, and q is p to the n, and q is not going to change forever. We're going to have the same fixed q for the rest of the talk. All right, so whatever q we're working with, there's all these bigger finite fields. There's this finite field with q elements, and there's also a finite field with q squared elements, and there's a finite field with q cubed elements, and they're all extensions of fq. And whatever finite field I'm looking at, because I have finitely many variables, there's only going to be finitely many possible solutions. If I have, 100 elements in my field, I know that's impossible, and I have 3 variables, then there's at most 1 million solutions. Okay. So because I have finitely many variables, this guy's a finite set. The set of solutions is a finite set. And so I can look at the number of solutions. That's just a number. All right. And I could do that for every n. And then I can make this function of S. Q again is the order of the field. This q to the n is the order of this field. It's the number of points in that field that I'm looking at. And to the minus s, because I'm doing a zeta function looking thing. And dividing by n for a reason that I'll explain shortly. Okay. So you can just sort of make this definition. You can look at all these numbers and make this formal power series and think about the exponential of that guy and wonder, does this converge? For which values of S in the complex plane does this series converge? It's some kind of series involving a complex number S. And it turns out it converges a lot of the time. It's, for normal zeta function reasons, the q to the n to the minus S grows pretty fast. Okay. But so what's up with the dividing by n and stuff? Maybe if we were curious about this sequence of point counts, we might want to do something more naive and say like, okay, what about just like a generating function, number of points over fq to the n, x to the n, something like this. The problem is that these numbers grow pretty fast, and so this is going to have very small radius of convergence. It's going to be tricky to study. And on the other hand, this guy has very good convergence. It's a pretty good guy. And there's something else we can say. The reason I'm dividing by the n is that if I do the logarithmic derivative of this zeta function, so by which I mean do the derivative of the zeta function divided by the zeta function, which is in other words, dds of log of the zeta function, that's the log cancels out the exp, and then I do the derivative inside the sum. And don't at me, anyone who does analysis. And so I get, let's see, I get this n coming down from here to cancel this guy. And so I get something like maybe I have like a log of q out front, a negative log of q, and then like number of points over fq to the n times q to the n to the minus s, something like this. I think that's right. And so this looks like maybe more, this is just a constant, and this maybe looks more related to that thing. So the logarithmic derivative of the zeta function is like more close to being a nice generating function. And the zeta function itself has magical powers. That's the point of the Weil conjectures. Okay, I don't want to spend too much time trying to motivate that because I don't have a really good way to motivate it, but that's the definition of the zeta function. And the true fact, because the Weil conjectures are a theorem, is that this has magic powers, and so I'll try to describe some of them. So here's one of the magic facts. This zeta function defined in this crazy way is actually a rational function. S is the variable here. S is a complex number. It's a rational function of that complex number. This is a meromorphic complex function. And we can even say more about the actual structure of the rational function. We know the factorization of the numerator and the factorization of the denominator as polynomials. There's like a really strong theorem here. But at a basic level, we know this is a rational function. And what does it mean that this is a rational function? Well, one consequence of that is that this guy will be a rational function. If you do, if I imagine I have like f over g, and I do log of that, I get like log f minus log g, and then I do the derivatives of those. Okay, I get something like a log of a rational function. And you can deduce from this that by normal generating function techniques, that these numbers satisfy some recurrence relation, some kind of like linear-ish recurrence relation. That comes from the fact that this guy's a rational function. And the degree of the numerator denominator will determine how complicated that recurrence relation is. Okay, so that's pretty cool. It's not an obvious fact. You might expect that they're like, you might have like some crazy variety defined in such a way that these have no observable pattern, but these numbers always have some kind of observable pattern. They're always satisfying some kind of nice recurrence relation. Okay, there's also a functional equation, which might be exciting if you like the Riemann zeta function. There's a functional equation for the Riemann zeta function, and this guy has a very similar looking thing going on. For any, I guess, positive integer k, this sort of reflection principle holds. And we don't have to care too much about what that is, but I should say E somehow is the Euler characteristic of your variety, whatever that means. So there's some kind of functional equation going on, like you see in complex analysis with the Riemann zeta function, where the coefficient out in front has to do with somehow with like the topology of this guy. And I can say what this Euler characteristic is really. It's because I started with a variety defined over Z, I could think about the set X of C. I could think about the solutions in complex numbers. And that's a set of points inside some high dimensional affine space over the complex numbers. It's a set of points inside C to the K. And so you can give it a topology. It has a subspace topology coming from C. And assuming we're smooth and proper, this actually gives us a nice closed complex manifold, smooth complex manifold. And the Euler characteristic of that guy is what I mean by this. So it's literally the Euler characteristic of the topological space. That's pretty cool. And it's an interesting thing because this zeta function only has to do with the point counts over finite fields. And the Euler characteristic only has to do with the structure over the complex numbers. And there's no relationship between those two things. A finite field does not map to C. C does not map to a finite field. But somehow those two kinds of things are related through the topology of the complex points. Okay. And then there's also a version of the Riemann hypothesis, and there's some way to compute Betti numbers of the complex points from the zeta function. And I'm not going to talk about those at all. But those are the other parts of the Weil conjectures. Yeah, Tomoki, I think something at least satisfies a linear recurrence relation. Like maybe it's the point counts divided by n, or maybe it's the point counts. I haven't worked it through exactly, but something like this. Okay. But so the point is that the Weil conjectures say that these point counts over finite fields, yes, q to the n, somehow have to do with the topology of the complex points, have to do with like actual topology ideas, manifolds and topological spaces. Okay.
Wait, could you
So
explain what do you mean like the Betty numbers on here? I'm
yeah,
curious.
I mean there's a way to compute the Betty numbers from the zeta function.
I see.
Yeah, the Betty numbers of the complex points. Sorry, there's lag on the drawing. All right. And the way is that you look at the zeta function, you look at the number of zeros and poles on a certain line, and that tells you the Betty number. It also comes from the rational function characterization. There's a whole bunch of things to say there. Yeah, but somehow there's this correspondence, and so they conjectured this at some point, and then many developments later, they all became theorems. And so some of this a little bit was by Weil, some of it in the special case was by Artin and other people, and Deligne finished off the last bit of the Weil conjectures. And now all the Weil conjectures are theorems. They're all true facts. Very exciting. But anyway, trying to prove these theorems required like developing new techniques. We had to somehow find a way to find a connection between the points over C and the points over FQ, even though there's no map between those rings, nothing like that. So we had to do something to get some topological information out of the values, the solutions of a variety over a finite field. You have some equations that could be interpreted over C over a finite field, and somehow just by looking at the solutions over a finite field, we have to be able to learn something about the topology over C. And so the way to do this was to develop some kind of theory of homology and cohomology over finite fields. And so that's the theory of Ital cohomology and L-adic cohomology, which we'll see later, but I will not explain. Okay. So now we're going to take a detour to a totally different topic that seems completely unrelated, but secretly is not unrelated because why else would I be talking about it in the same talk? And the other topic is counting fixed points. So imagine I have a function from the real line to itself, and I want to know how many fixed points does that function have? In other words, how many points are there where f of x equals x? It can happen sometimes, maybe it happens 100 times, maybe it happens never. But equivalently, what I'm saying is let's draw the graph of f. Here's an example picture, and look how many times the graph crosses the line y equals x. And that's the number of fixed points. Cool. All right. There's something else I could do. Well, okay. So that's like a literally true thing. If you want to do this using algebraic topology techniques, things get a little bit tricky because sometimes I could take two functions that look very close to each other and they'll have very different fixed point counts. So I could take this function and just move it a little bit, and it looks like the number of fixed points is staying the same. That's fine. But if I move it too much, then suddenly I have no fixed points left. And it's like all kind of the same function, just shifted around a little bit. And if we wanted some kind of purely algebraic way to compute the number of fixed points, it might be kind of tricky if things are sort of changing non-continuously in this way. I sort of translate the same curve around and suddenly it has fixed points or not. So, okay, we sort of do know how to do this for parabolas like I drew. But in general, this can be kind of a challenge. And sometimes even I'll have exactly one fixed point, which I'll try to do here. But it like has multiplicity too. There's sort of a double intersection right there in the same way that like every quadratic polynomial over C has two roots, but sometimes they're the same root. Okay, so the idea to count fixed points is to, instead of just counting the number of fixed points, we're going to associate to each fixed point an invariant called its index. And so in this original picture, I had these two fixed points. And this one is going to have index +1, and this one's going to have index -1. And I'll explain what that means. So if you have a fixed point in general, there are sort of a few different ways that could happen. So here are three different ways you could have a fixed point. Maybe the curve just goes through the diagonal line, transversely increasing, having an intersection like this. Oops. Maybe it goes through and it's like decreasing, I don't know why that keeps coming back up. All right. Or maybe it comes up and then bounces off and comes back down. But in any case, what I'm going to do is look at this window. I'll just erase this tape here. Okay. Great. What I can do is look at a little window around the fixed point. So here's my fixed point. and I've got these like pink lines above and below. And I'm going to look at in that little window, when I started at the bottom in my domain, did I end up at the bottom or the top in my codomain? So in this first picture, when I start at the bottom in the domain ends up at the bottom in the codomain. And the top in the domain ends up at the top in the codomain. But in the other picture, the order is reversed. The first point in my domain ends up at the top in the codomain. And the second point in the domain ends up at the bottom in the codomain. And in the third picture, the first point in the domain ends up at the bottom, and the second point in the domain ends up at the bottom. And there's also a fourth picture I could have drawn where it starts at the top and ends at the top, where it bounces and goes back up. And so this guy, where the order is preserved, I say that's index +1. This guy, where the order is switched, I say that's index -1. And this guy, where both things get sent to the same, I say that's index 0. And the reflected picture also has index 0. And now, no matter what I do to my parabola, no matter how I move it, the number of fixed points, if I add up their indices, stays the same. The video share really is lagging. I'm moving this in a much more interesting way, I promise. Okay. So, but no matter what you do now, we started with an index of +1 and -1. I could shift it so that I have an index of 0 by having the curve just bounce off. Or I could shift it off of the line completely so there's just no points. And no matter what I do, when I add up the indices over all the intersection points, I get 0. Okay. And so this sort of notion, adding up the indices of the fixed points, is invariant under perturbations of the function. And so it's plausible that we could try to compute this sum of indices of fixed points using some kind of algebraic topology technique. And the answer is yes, we can. So that's a theorem of Lefschetz. And I'll just state the theorem here. Hopefully it fits on the screen, almost. Okay. So if you have a function from a closed manifold to itself, so like maybe from S1 to S1, or like from R to R, but then it doesn't quite work because R is not compact. You have a function from a closed manifold to itself. If your function has, let's say, a finite number of, sorry, not isolated zeros, isolated fixed points. If your function has isolated fixed points, so let's say a finite number of fixed points, then adding up the indices of those fixed points is equivalent to computing this alternating sum of traces of the action of your map on the cohomology groups of your manifold with coefficients in Q. So that last part was a mouthful. But all I want to say is from your closed manifold M, you can somehow produce these vector spaces. These are things you can compute. This is a vector space over Q. Just a symbol for this weird vector space that I could compute starting with my space. And when I have this map from M to M, it gives me a linear operator on that space. And when I have a linear operator on a vector space, also this will turn out to be finite dimensional because M is closed. When I have a linear operator on a finite dimensional vector space, I can take its trace. And I have one of these for all I greater than or equal to 0. It also turns out this sum is finite. Eventually, these groups vanish once you're past the dimension of the manifold. So this sum always converges, and it's just a sum of traces of linear operators. And you could always, in almost any example, you could sit down with your manifold and think carefully enough and compute the dimension of this vector space and find a matrix representation of this map and add up the diagonal entries and do an alternating sum of those traces. And you would get this number L of F called the Lefschetz number, which is not literally the number of fixed points, but it's close. It's the sum of the indices of the fixed points. So, if all the indices happen to be 1, it would be the number of fixed points. That would be nice. Okay. I also didn't explain, I drew this picture about index in a situation where I map from R to R in a one-dimensional situation. And there is a notion of index in any dimension. A map from Rn to Rn at any fixed point also has an index, but it's defined in secretly the same way, but in something that's harder to draw. Okay. All right, so that's the Lefschetz fixed point theorem. I will pause here for questions, thoughts, feelings, etc. How's it going out there? All right, cool. Okay, so let's talk about the Frobenius. I spoiled a little bit there. All right. So if I have this number q, which is a prime power, there's a field with q elements. Inside that field, there's this map where I could just raise everything to the qth power. It's a perfectly fine thing to do. But this actually turns out to be the identity function on fq. And the reason is just that inside fq, okay, first of all, it's true for 0. 0 maps to 0 to the q, which is 0. Good stuff. And for anything non-zero, I'm living inside the group of non-zero elements under multiplication. That group has order q minus 1. So when I raise something to the q minus first power, I get the identity, which is 1. And then when I raise it to the qth power, I'm back to myself. So in both cases, we're good. So it's really the identity map. And so, okay, cool. That map is the identity map, and so it's definitely a ring homomorphism. But actually, it turns out it's even better. In any field of the same characteristic, raising to the qth power is a ring homomorphism. It might not be the identity, but it at least is a ring homomorphism. And this comes from, like, I don't know, you do your favorite binomial theorem argument. And so there's this map on any field of characteristic of the same characteristic as q that sends everything to its qth power. And I could take the algebraic closure of fq, sort of the union of all the finite fields, fq, fq squared, fq cubed, fq to the fourth, all of those, take the big union of all those guys. And that is a big field that has this endomorphism, raising everything to the qth power. And the theorem is that the fixed points of this map on the algebraic closure of fq is precisely just the things that lived inside fq. Anything in a bigger field was not fixed by this map. So why is that? So first of all, everything in fq was fixed. This was the identity map on fq. That's good. On the other hand, anything that's fixed by this map would be a 0 of this polynomial. But this polynomial has, at most, q solutions in any field. Polynomial degree q has at most q solutions. And I found q solutions. It was all the elements of fq. So that's all of them. Proved. All right. So the fixed points of this q Frobenius are precisely the elements of fq. And this says something else. If I had a scheme defined over Z, and I think about the points in fq bar inside the algebraic closure of fq, those points are just like, I have a bunch of values for my variables to be, and they satisfy the polynomial equations. And I could apply this Frobenius map to all of those values. All my variables had assignments, and I just raise all of those assignments to the qth power. And the fixed points of that Frobenius map will be precisely the solutions over fq. To be fixed by this, for a solution to be fixed by Frobenius, it means that all the entries were fixed by Frobenius. It means that all the numbers came from fq. So in the proof of the Weil conjectures, when we're trying to like go and prove stuff about this zeta function, we care a lot about understanding these point counts, number of points over fq, and how can I try to get a handle on these guys in some kind of topological way? This is also the number of fixed points of the Frobenius map on this kind of space. Okay. And so that was like the real major insight that allowed us to, well, I say us, but I was not born. This was the major insight that allowed people much better than me at algebraic geometry to resolve the Weil conjectures, which is if you could somehow find some kind of way to control the number of fixed points of a map, you could count these solutions over finite fields. Okay. And here's another fact, which I will not explain. All of these fixed points of Frobenius are going to be, they're going to be isolated fixed points, and they're going to have index 1, whatever that means. So in our Lefschetz trace formula, the plan is going to be to do a Lefschetz trace formula. If we could try to count these fixed points by just saying, we try to count these fixed points by just saying, okay, it'd be cool if they all had index 1, then this would be the number of fixed points. And in this case, this is true somehow. All the fixed points of Frobenius they're isolated fixed points, all of index 1. This comes from the fact that the derivative of the Frobenius is 0. Anyway, and so, okay, so all these fixed points are isolated of index 1. And so this kind of formula, we should be able to come up with some kind of formula like this to count the number of points over FQ, where somehow this trace is going to be acting on, instead of M, it's going to be like the set of solutions over FQ bar over the algebraic closure. That's what we were acting on to get our fixed points. So somehow we're going to try to come up with a formulation where this guy is my manifold, and then I have cohomology groups of my manifold, and I take the action of Frobenius on those cohomology groups, and I take the traces of those, and I do an alternating sum, and I get the number of points over FQ. All right, and so theorem, you can do this. So here's Grothendieck's trace formula. Right. So Grothendieck said, okay, yes, this does work. The number of points over FQ is the number of fixed points of this Frobenius. That number of fixed points of Frobenius is counted by a formula like the one we had. My manifold is like the points over FQ. Maybe I'll over FQ bar. Maybe I'll indicate that here. I take coefficients kind of in the rational numbers, but actually in the L-adic numbers, it doesn't matter. It matters a lot, but we're not going to talk about it. And we use this cohomology theory called a tall cohomology with compact support. Whatever that means. And I'm not really going to say what that means, but it is a thing you can do. Instead of starting with a topological space and computing the cohomology of the topological space, you can start with a scheme and compute the Étale cohomology of the scheme. And the scheme is just the data of like names of variables and polynomial equations. It's not a space, but just from that sort of like algebraic combinatorial kind of information, you can define these Étale cohomology groups in a purely algebraic way. And it's true that you'll get an action of the Frobenius map on those cohomology groups. And you can take the traces of those actions, and you can take the alternating sum of those traces, and it will give you the number of fixed points. All right. Cool. The only other problem is that cohomology with compact support is annoying. So we're going to do a little Poincare duality. You don't have to understand any of that, but it just turns out that this line is equal to this line, where I do Étale cohomology, but an easier form of Étale cohomology. And I do the alternating sum of the traces of Frobenius on that guy. But it's actually the dual action on the dual group. And I have to pull out this factor of Q to the dimension of X, whatever that means. All right. That's just going to be a useful computational tool for us later. But it turns out to be like completely formal. It just follows from like completely abstract algebraic topology theory.
Wait, so is it the homology theory that if you take dual?
Well, yeah, it's like that. It's actually a little different. The problem, the real trick here is that when we do this dualization, we change the Galois representation.
Okay.
And so the action of Frobenius is going to be different.
Oh, I see. Like, and is it typo or like purposefully like you didn't put FQ on the bottom?
Oh yeah, I mean there should be it should be the base change to FQ. It's true. It should be the base change to FQ bar, and sorry, it should be a subscript FQ bar, and this Frobenius is the relative Frobenius of the base change to FQ bar, whatever that means.
Okay, I see. Yeah.
Yeah.
Mm.
Okay. All right. So we have hypothetically this formula. The only problem is we have no idea how to compute these guys, and we have no idea how to compute the action of Frobenius. Great. So if we could do those things, then we would just add up the numbers and we would know the point counts. But that turns out to be kind of tricky to do. So here's a nice theorem that helps us a little bit of the way there, which is this Étale cohomology group has the same dimension as the ordinary cohomology of the set of complex points as an actual topological space with coefficients in the rational numbers. This is like dimension over QL. This is dimension over Q. But this vector space and this vector space have the same dimension. And so that at least gives us some place to kind of start. You have a trace of a matrix. It's the sum of the diagonal entries. How many diagonal entries are you summing? It's the dimension of your vector space. So this tells us at least something about what's going on, because I can try to compute these guys. The set of complex points is literally a topological space. And So maybe there's some hope to try to compute these dimensions. And it's, you know the dimension of the vector space, you have a linear transformation on it. You can't say very much about the trace. The trace could be anything. But maybe we could get a little more magic about how this guy acts, and then we'd be happy. All right, and so that's what's going to happen. We're going to get some more magic. I should also say the dimension of this space is also the same as the dimension of its dual. So that's fine. Okay, sometimes, like in the example that we're going to consider later today, the action of Frobenius is by a scalar. It's actually just multiplication by a scalar on the vector space. People use the letter L. I'm not sure why exactly it's L, but you need to do coefficients in the L-adic rationals for some prime L, which is co-prime to Q. So it's important that so you pick some prime L to begin with that's just different from the characteristic of your base field, and then you have to use QL. But it could be R, yeah. But we already used P, we already used Q, so. All right. Arden's theorem not depend on reduction on P. I think it's still true. I don't know. I'm not an expert. You don't cite me. I think Arden's theorem holds for all varieties defined over Z. But I'm not sure. Okay. And by variety there, I do mean separated finite type integral. Yeah, soon I'm going to move to like an affine example. So, but all the stuff I've been saying here does hold for affines. Like this trace formula with compact support holds for affines, and Arden's comparison theorem holds for affines. So I really just need for the stuff that I've been saying so far, it works for yeah, finite type separated. Yeah, varieties defined over Z. The weird part is, so for experts, Deligne proved that the eigenvalues of Frobenius on these spaces are Weil numbers of a certain weight. And for smooth proper varieties, that's true. And for other varieties, that's not necessarily true. The weights can be different. But it's still true that the trace formula holds. You don't need algebraic with closed Brownian field. No, defined over Z. And this guy, sorry, this guy is, X base changed to FQ bar. Okay. But you do need it to be defined over Z in the first place, or maybe Z localized somewhere to be able to go to C and to be able to go to FQ bar. All right. So anyway, this is going to be true in our example. It's going to be true for us that when we compute this sum, this action of Frobenius on this ith cohomology group is going to be multiplied by Q to the minus I, sorry. The minus is because of the dual, and the I is because of the I. And so that's going to be a true fact. And so this trace is going to be just this scalar times the dimension of the vector space, which we know is this dimension. Great. So we're going to get this kind of formula. This is going to hold in the example that we talked about today. All right. So that's just putting together all the things we've learned / accepted for free. All right. And so now we're just going to do this. But we're actually going to do this in sort of the reverse direction. What we're going to do is actually compute these numbers directly in a particular example. And then we're going to deduce these numbers. And we're going to learn for free the cohomology of certain spaces. Okay. So here's the variety we're going to think about that we're going to apply this technique to. It's called the configuration space on endpoints. So it's a system of polynomial equations. It's a variety. It has finitely many variables. It has exactly n+1 variables and exactly one equation. But the t is really a dummy variable. What's going on here is I want to think about the space of degree n monic polynomials which have no repeated roots. So how do you tell if a polynomial has no repeated roots? You look at the discriminant for like x squared plus bx plus c. The discriminant is b squared minus 4c. And if this is 0, then there's repeated roots. And if not 0, then there's no repeated roots. And there's a similar expression for any degree of monic polynomial. For a 7th degree monic polynomial, there's an expression for the discriminant, which is a polynomial equation in the coefficients. And if that discriminant is 0, then you have repeated roots. And if the discriminant is non-zero, then you do not have repeated roots. And so to look at the space of monic polynomials of degree n with no repeated roots, I just want the space of degree n monic polynomials where the discriminant is not 0. And so to make the discriminant not be 0, but write that as a polynomial equation, I say that there's something that I could multiply the discriminant by to get 1. Okay, so that really is a variety. And so here's another way to say that. It's the tuples I could have that are the coefficients of a degree n monic polynomial. So the discriminant of that polynomial is not 0. And that's the same as the space of separable monic polynomials degree n. Separable means no repeated roots. Okay. Should note, if F is an algebraically closed field, then the points of conv n over F, well, any monic polynomial of degree n will have exactly n roots in F. It'll give me n numbers in the field F, and they'll all be distinct. This is also the set of subsets of F of cardinality n. This is the space of subsets of size n inside F. And the points I get don't have an order. The coefficients have an order, but the roots of the polynomial don't come in an order. All right, so that's what this configuration space is doing. And so, for example, if I think about conv2c, I think I made a typo here. Da 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 da. That. I think that's right. That's just the two coefficients with the condition that the discriminant is non-zero, which is what I wrote before. But this is also, the set of ways to have 2 points in R2. R2 looks like C. Having 2 points in R2 is like having 2 complex numbers that are distinct. This is the space of subsets of R2 of size 2, if you like. That's the topology on this space. And okay, what about the configuration space of R? This is where I have, oh no, it has a piece that looks like R2 where the 2 numbers are distinct. And it also has a piece where the 2 numbers are distinct complex numbers of that are in a conjugate pair. So it's maybe like this guy plus a C minus 0 or something like this. Divided by 2? Man, okay, don't worry about it. Erase that example. All right. But sometimes over finite fields, this gets easy to tell. So like conv2, the points over F2, these are polynomials of degree 2 that are monic. They have coefficients in the finite field with 2 elements, and they have no repeated roots. And there's exactly 2 of them, and there they are. Those are the 2 polynomials which satisfy that condition. All right. Cool. So now we're just going to compute all of the point counts directly. For any finite field FQ, we're going to figure out exactly how many points does this variety have over that finite field FQ. How many solutions are there? And the claim is this. It's going to be given by this formula. If n is 0, I'm thinking about degree 0 monic polynomials. That's called the number 1. And there's one of those. Great. I could also think about degree 1 monic polynomials. That's where I have x minus r for r my root, and I want the roots to be distinct. All good. It could be anything. So this is the number of elements in my field. And when n is at least 2, it's going to be given by this formula, q to the n minus q to the n minus 1. All right. So let's prove it. So let's call this guy a sub n. And this is the part where I have to thank David for helping me work through this argument. Okay. So what I'm going to do is a sub n is the number of separable monic degree n polynomials with coefficients in FQ. So what I'm going to do is think about the non-separable monic polynomials. So there's q to the n monic polynomials of degree n. And if I subtract an, that's the number of non-separable monics of degree n with coefficients in FQ. When I have a non-separable monic polynomial, it has to factor in a particular way. A non-separable monic polynomial means that when I factor it into irreducible polynomials, I have some irreducible polynomial appearing at least twice. So what I can do is take my non-separable monic and write it as r times s squared, where r is monic and separable. It has all the unique irreducible factors. And S is monic, but not necessarily separable. S has all the repeated factors. And if I have something appearing 5 times, I take 4 of those copies and put it in S as 2 copies squared. And I take the remaining copy and put it in R. So that'll happen, and S will be monic of some degree, at least 1. If S had degree 0, then F would have actually been separable. Okay. So the nice thing is that this factorization is completely unique. I know there's only one way to do this. R has to contain all the distinct prime factors, and S has to contain everything else. So, sorry, maybe R doesn't contain all the distinct prime factors. R contains all the prime factors that occurred an odd number of times, a distinct version of each of those, and S contains everything else. Okay. And so I'm just going to add up over all the possible degrees of S. So that degree could be 1, or it could get all the way up to n over 2, floor n over 2, or whatever, because I'm doing S squared. And then R has degree n minus 2d, because we did S squared. And R is monic and separable, so that's going to be an A n minus 2d. And times how many monic polynomials are there of degree d is q to the d. And so I get this recurrence relation when I say go up to n over 2. If n over 2 is half an integer, go up to floor n over 2. That's what I mean. And this recurrence relation is true. And the other nice fact is that this guy satisfies the recurrence relation with the right initial conditions. I guess you have this recurrence relation for n at least 2, and you check the base cases. Okay. Okay, I think for the sake of time, I'm not going to go over that. But it's kind of fun. It's a little telescoping argument. You just plug in, you plug in this formula here. You have this edge case where you get to the edge thing over here, and everything like works perfectly. Yeah, if you check, it's really nice. All right. So blah, 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 induction. Wow, it's true. Okay. All right, so you get this recurrence relation. You verify the recurrence relation. We have a formula for the number of points in the configuration space over FQ. I left a lot of space to fill in that proof, but we didn't actually do it. But so now let's put it all together. We have this formula that says I'm going to have a q to the dimension of x, alternating sum of q to the minus I, dimension of these cohomology groups to get the number of points over FQ. And we need to know the dimension of this configuration space. It turns out that number is n. And the idea is just that we haven't defined what does dimension mean. But the point is that this configuration space, if you think about like conv of C, for example, it's like C to the n minus the set of points where the discriminant is 0. That's a closed set. So that's an open set. That's a closed set inside C to the n. So that's an open subset of C to the n. So conv of C is this like open submanifold of C to the n. It still has dimension n as a complex manifold. And you could do the same kind of argument over any ring. In other words, to describe a point inside conv n, I need to give you a separable monic polynomial of degree n. I need to describe all n coefficients. I have n degrees of freedom. Okay. Cool. So that's the dimension of this space. And so I can just plug this in. So here's what we got. First of all, this number we computed by hand for n at least 2. But also that equals this alternating sum, where I factored the q to the n, q to the minus I, turn that into a q to the n minus I. Okay, cool. Great. But now, here's the thing to notice. This holds for all q simultaneously. This is true for every prime power q. And this is a polynomial in q. And this is also a polynomial in q. It turns out the conv of C is a finite dimensional manifold, so the homology groups terminate after a certain point. These are both polynomials in q. Or sorry, yeah, and they agree for whenever q is a prime power. Whenever q is a prime power, so it's an order of a finite field, these two polynomials are the same. And there's an infinite number of prime powers. And so these are two polynomials defined over Z that agree at an infinite number of integer points. So they're the same polynomial. The coefficients are exactly the same. And so we immediately deduce the dimensions of these cohomology groups. We know them all. Most of them are 0. The coefficient in front of q to the n is 1, and the coefficient in front of q to the n minus 1 is also 1, and the rest are 0. And so that's the dimensions of h0 and h1. Compare. So we conclude for free the structure of the cohomology of these configuration spaces with rational coefficients. And this was something that was computed by like Arnold directly. It computed all the homology groups of these configuration spaces and started this whole industry of doing like homological stability results and representation stability and lots of interesting stuff there. Um, but this kind of slick proof allows you to avoid ever really thinking about the manifold confen of C. You don't have to like put a cell structure on it or anything. You just count the points over a finite field, and then you compare two polynomials, and you know the dimensions of the cohomology groups for free. Um, so that's the main result I wanted to present. Yeah, I'd hope to say a little bit about braid groups, but let's stop there. Thanks for coming. Okay. Any questions for me? Look, yes. Could you review the definition of convet? Yes. I can scroll up to it. Here's this guy, and I can write out what it is as a variety. Confen is spec z adjoin x naught through xn minus 1. Adjoin the discriminant inverse. It's this guy. The discriminant is the discriminant of the polynomial, which has these coefficients.
Right, so
Conven, yeah.
these variable are corresponding to the coefficient of the equations.
Uh,
So the xn minus r minus 1 are coefficient of the equations.
so confen, the points of confen are going to be polynomials.
Yeah.
So yeah, and so the coefficients of the polynomials are these guys, the x0 through xn minus 1.
Yeah.
And then I formally invert, I join delta inverse, where delta is the discriminant of that polynomial.
Yeah, so like discriminant means that like thinking as a one variables, and like these are some hyperplane like I mean single equations, right? Like single equations to when it is vanishing when there is a multiple roots or
Yes.
something. Yeah.
Yes, yeah. So I have, yeah, exactly. So conf2.
Okay, it makes sense. Yeah.
Yeah.
Um, I see.
Do these methods extend to showing homological stability for configuration space of, say, projective varieties? I actually have no idea. It would be really cool to find out.
Uh, I what are you trying to say about the braid groups?
Oh, I just wanted to say from here, you can also deduce, once you know these cohomology groups, this implies, for example, that confen of C, which again is I should say, confen of C, the point is this space is interesting because this is the space of subsets of R2 of size n. In other words, it's the space of possible configurations of endpoints inside the plane.
Yeah.
Yeah. And so like pi1 of this space is the braid group on n letters. Because if I have a configuration of 3 points in the plane and I try to make a loop in my space of configurations, I have to move my configuration of 3 points around and somehow end up at the same 3 points. And by doing so, I'll send each point will sort of end up somewhere. And I have no way to draw this well. But you can imagine the 3 points sort of like twisting around each other in weird ways to end up down there. And you end up with a braid. A loop inside this space is a braid. And so the braid group on n strands is the fundamental group of this space. And from this computation of the cohomology, you can
Yeah.
deduce basically you can deduce that the abelianization of the braid group is Z. You have to worry a little bit about torsion, but you can figure it out. So that's an interesting fact. It's not like super obvious ahead of time that the abelianization of the braid group is Z, but it is true. Okay, and it's almost follows from this cohomology computation. You have to do a little more work, but at least you know it has rank 1, the abelianization by Hurwitz. And what else is true? You see from this description that the universal cover of the configuration space is going to be weakly contractible um, by something stellar approximations. And as a result, the configuration space itself has no higher homotopy. So you also get that conf C is a KBN1 space. It's an island original plane space for the braid group. You also get that from this cohomology computation. That one really does follow. So you get these like nice facts about the braid group. It tells you that this configuration space is not just a group that has this fundamental group. It's sort of the space that represents the fundamental group topologically. Represents this braid group as a topological object. So it's a really nice space to study. And it has magical results about homological stability, but I don't know very much about those.
I see, because I wasn't sure that like equivalent formulation of the configuration space in this definitions and like the definition you provided earlier.
Mm-hmm. Yeah, they are equivalent. The set of points of confen over the complex numbers is this space. If you take the analytic topology on the complex points of confen, you get exactly the actual configuration space of endpoints in the plane. And those really do agree as topological spaces. Over a finite field, the points of confen over FQ are not just collections of endpoints in FQ, because polynomials in FQ don't always split. But over C, the polynomials always split. And so having a polynomial is the same as having a bunch of numbers, and having a bunch of numbers is the same as having a bunch of points.
Okay, I see, I see. So that makes sense. Yeah.
Yeah. Cool. All right. Thanks everyone for coming.